This is the final part of the series on backlash, deflection and vibration on the Shapeoko. In this part we'll put together the deflection modes from part 2 with all the measurement data. First we'll go through the big 3 deflection sources on the machine: the baseboard, the dreaded V-wheels and the belt system. For each of these we'll look at how they occur and then use the measurement data to understand how much unwanted movement they allow. We'll also see how they vary between the different sizes of machine. The belt system turned out to be somewhat more complex than I expected, so that needs a bit more detail. Stepping up from just measuring tension, we'll try to understand more about how the drive belts work. We'll see what affects belt deflection, how backlash occurs, and see how the belt deflection varies with position. Finally, we'll have an overall deflection model of the machine. This will show us what the overall behaviour looks like, how that varies with X and Y position, how different the Shapeoko 3 and XXL are, and what impact a couple of sample upgrades might have. Our first suspect for deflection is the notorious baseboard of the XXL machine. Starting with the frame, whose main purpose is to hold the Y-rails square to each other and level above the baseboard, the front and rear metal frames are linked by 3 steel cross straps. This is then topped and held square by 2 18mm MDF sheets. The frames and steel straps are both folded to provide some rigidity, but this is limited over the width and depth of the XXL. Calculating the expected deflection for one of the steel straps under a 5 kg weight in the centre yields 2.2mm. This is consistent with what I've measured on my machine before bolting the baseboard down to something more solid. The most visible issue to most users appears to be sagging of the baseboard over time, which results in the spoil board losing flatness. The underlying cause is the lack of rigidity in the baseboard support straps. If we're concerned with deflection and vibration though, holding the workpiece still is a good place to start. Remember that there are vertical forces in cutting as well as horizontal, and vertical movement in the workpiece can interact with the nodding mode of Z-axis deflection. In what is a recurring theme, the standard size Shapeoko 3 produces a calculated 0.27mm deflection for the same weight versus the 2.2mm on the XXL. Score 1 for the Shapeoko Pro. As replacing the MDF with a 10mm aluminium sheet is quite a popular upgrade, a quick online calculation suggests that for the same 50 Newton load in the centre, even without the steel straps this would only deflect 0.2mm on the XXL and 0.02mm on the standard Shapeoko 3. Second suspect, the V-wheels. Our next significant source of deflection in the machine is the V-wheels. These allow linear motion along the X and Y axes. In an ideal world, these would be frictionless and only allow movement in one direction. But we don't live in an ideal world. However good our drive belts are, they can't make up for the additional movement allowed by the V-wheels or ignore the rolling resistance. Assuming you've already upgraded to the Z Plus or HDZ, the first set of V-wheels are those responsible for mounting the Z carriage to the X-axis rail. These are under the greatest stress and also responsible for much of the linear motion deflection. I found 2 main modes of deflection in the X-axis V-wheels. The first is rotation of the Z carriage about the Y-axis. This is allowed by radial play in the V-wheels. When vibrating, this rocking motion only needs to rotate the Z assembly, and with the centre of rotation close to the centre of mass, this further reduces the ability of the V-wheels to resist. This vibration mode is likely excited by deep cuts traversing along the X-axis. The resonance for this mode is rotational and likely higher frequency than the linear belt resonance mode. Consider shaking a can of beans by twisting versus up and down, although neither case is desirable for the beam. The second is a nodding movement where the Z-axis rotates around the X-beam. This is allowed by axial play in the V-wheels where they're less effective than in radial. This nodding movement is more displacement than rotation, and therefore the spindle and Z-mass take more force to move. This mode is excited by deep cuts moving in X or Y axes and vertical forces generated by the helix on cutters. As this mode changes cutter vertical engagement as well as radial, it can be quite violent in terms of cutting force changes and resulting vibration modes. For both of these modes, the small spacing of the Z carriage V-wheels means that cutting forces are amplified and have high leverage over these wheels. This also suggests that stacking the workpiece up towards the X-axis on additional spoil boards, vices or jigs may help to reduce some vibration modes. A common response to this unwanted movement, certainly mine initially, was to increase the preload on the V-wheels. This initially ensures that there's no gap and then starts to deform the V-wheel onto the rail, making the assembly feel more rigid and increasing the effective spring force of the wheels. One outcome of this is to reduce the deflection for applied cutting forces, but this only works up to a point and comes at the cost of increased rolling resistance and eventually lumpy or broken V-wheels. The second sets of V-wheels are on the Y-plates at each end of the X-beam. These show much less deflection, 0.02mm for 50 newtons left and right and X. I think that these wheels contribute less to the overall deflection and vibration for a few reasons. There are 8 of them, not 4. They're spaced further apart and therefore there is less leverage over them, and the additional mass of the X-beam and steel Y-plates. So, how much deflection? On my machine at a reasonably high preload, the table shows the numbers I measured. Overall, the V-wheels contribute a major part of the total deflection, even more so on the smaller machines. Increasing preload can reduce deflection a little, but at the expense of early wear out and increased backlash. I have no recommendation on how tight or any sensible way to measure the preload. Third, we have the drive belts. The Shapeoko drive belts are responsible for a significant part of the overall deflection, and, as before, more deflection on the larger machines. In particular, the belt on the X-axis is likely to play a significant part in spindle vibration by allowing the Z carriage to move left and right as it stretches. This is in addition to the rotation movement from the V-wheels. It's useful, therefore, to understand how the drive belts work. To do this, we can produce a simplified model of the belts as used on our machines. The first element is to find out whether the drive belts exhibit the same bowling ball in a box type backlash as a ball screw, lead screw or rack and pinion system. Well, they do, but only a tiny amount. According to the Gates data, and our belts are the 2M PGGT3 type, only around 1 or 2 tenths of a thou, that's 0.005mm in sensible units. This is pretty impressive, but then this belt geometry was designed for positioning applications, and therefore it does absolute position pretty well, assuming you did up all your set screws properly. The drive belt system on the Shapeoko relies on belt static tension to work. The belts are tensioned between anchors at each end of the main axis rails, and the belt starts with a nominal length, but is then stretched to achieve a static tension on the machine. This works because the belt stretches elastically. For each increase in applied force, there's a proportional increase in belt length. Note that this is a proportional increase in belt length, so a belt twice as long will show half the tension for the same extension. This property of the belt is called the tension modulus, and we have a series of measurements of this value for different types of belt. To drive the axis, the belts pass around a set of idle bearings and over a toothed pulley on the drive motor. As the stepper and tooth pulley prevent the belt moving relative to the driven axis, we effectively have 2 sections of belt. Each is anchored to one side of the moving axis, with the same static tension as the axis is free to move along the rail. This is the resting state of the belts, equal tension either side of the moving axis, and to satisfy Sir Isaac Newton, no net force on the moving axis. The system is in an equilibrium condition. When we apply an additional force, either by driving the stepper motor to move the axis or a cutting force from the spindle, the system needs to find a new equilibrium state where all the forces cancel out again. When this happens, the belt on one side gets shorter while the belt on the other side gets longer. This results in a net force from the belts, which either overcomes friction to move the axis or resists a cutting force. The larger the deflection, the greater this force. One complication is that, as we know, the stretch of the belt for any given tension is proportional to the length. So for any deflection, the longer side of the belt is going to show a smaller change in force, and the shorter side a larger change in force. This means that as we get close to either end of the axis, the short side belt will produce sufficient restoring force for less deflection distance. So, how does the belt drive behave then? We can use the equations from those diagrams to see what impact all this has on the deflection. These charts are based on the 9mm Kevlar belts on my machine and the observed tension modulus on that machine. I'm seeing approximately 0.018% extension per 10 newtons force. This is lower than that previously measured by the real J. Anderson for the Kevlar 9mm belts. This difference may be due to batch variability, or it may be due to rolling friction on the axis reducing the apparent tension. There are a few things we can see from these simplified models. The belt deflections are largest in the middle of the axis travel. The long axes of the XL and XXL have more belt deflection in their longer belts, and the belt deflection seems to be linear with the applied force on the belts. The type of belt in use also has a substantial impact. We have tested all vendor data for quite a range of belts. Based on that data, this is the belt extension at XXL length and 10 newtons force. Note the 15mm fiberglass GT2, which is the type of belt apparently installed on the Shapeoko Pro. This has only slightly better deflection performance than the 9mm GT2 steel belt, however it does not have the earlier failure problem when flexed around small radius drive pulleys. The 9mm Aramid Kevlar belts still appear to be a good option for the non-pro machines. The other important element in the belt and backlash behaviour is the axis movement friction. On my machine it takes between 0.5 and 1.5 kilogram pull to move the x-axis, around double this to move the y, predictably enough as there are twice as many V-wheels, belts, etc. Note that if you measure this, you need to release the belt anchors as there's significant additional movement resistance from the belt and motor system. When our machine moves, it must overcome both the cutting forces and the friction of the moving axes. This results in a certain amount of wind-up or pre-tension in the belt to overcome this friction, which is what manifests as backlash in the machine. Here I'm manually deflecting the x-axis by pushing on it. We can see that there's no apparent lost motion between the local section of belt and the V-wheel of the axis. Testing my Z-carriage, I was able to measure the following behaviour as I increased tension on the V-wheels. This produced a range of rolling resistance and therefore varying backlash. This rolling friction causing backlash is as good a reason as any to not over-tighten the V-wheels on your machine. One possible source of backlash is if the belts do not immediately elastically recover when the tension force is reduced, a belt memory effect. This effect is difficult to measure. I performed a simple test to look for this by running the axis into a hard stop and then making the machine take some additional steps to increase the belt tension and extension. This was well within the belt stretch available from the stepper holding torque. I then stepped the machine back away from the hard limit to observe whether it took any time to recover to its previous step positions. I was unable to observe any evidence of slow recovery within the belts, but this experiment was not particularly well designed. So what size backlash can we expect? Well, taking our measured friction of 10 newtons, we would require somewhere between 0.02 and 0.2 millimeters of belt deflection to overcome this force. That depends on the axis size, the type of belt, and how enthusiastically the V-wheels have been tensioned. It's not just a simple rolling resistance value. I expected this to be a relatively simple rolling resistance from the V-wheels, which would give a constant force required to move the axis any distance at any speed. This is not what I observed, and I don't have an effective explanation or model for the behaviour I found. Testing the backlash by reversing direction and moving down from 1 through 0.25 to 0.025mm step sizes. At the 1mm step size we see 0.03 to 0.04mm backlash on this machine, so we'd expect to lose an entire step at 0.025mm. That's not what happens though. What we seem to have instead is a force required to move the wheels and bearings which depends on the distance they're being moved. This is presumably some element of plastic deformation as the wheels roll. The chart shows deflection on the x-axis for 4 different V-wheel tensions. Aside from the increasing backlash around the zero, there's no other significant variation at this measurement accuracy. One interesting experiment is to disconnect the drive belts and use a weight and pulley to pull the Z-carriage along the x-axis of the machine. We might expect this fixed force with just enough weight to overcome the rolling resistance to smoothly move the Z-carriage across the machine. This isn't what happens. As they roll, the V-wheels show significant variation in observed rolling resistance. This varying resistance is likely to affect both precision of movement and backlash by requiring different belt extensions to move at different points on the axis. Measurement time. So, we have some ideas about what's going on, but now it's time to get some real data from the machine. We have a model of the belt behaviour, but for that to be useful, it must make testable predictions about the machine. First, I measured the x-axis slop, deflection and backlash due to the belt system at 12 different positions across the x-axis. To isolate the belt deflection and minimise the contribution of other sources such as the V-wheels, these measurements were made between the X-rail and the side of the HDZ close to the X-belt. Force was applied to a rod clamped in the collet where the machine would normally see cutting forces, and V-wheel tension was set to give just over 10 newtons of rolling resistance. To provide a repeatable force, a cord was attached to the rod and hung over a pulley suspending a 5 kilo weight. At each location, the slack was measured by moving the rod left or right by hand, and then observing the distance between where it came to rest when the force was removed in each direction. Before the deflection measurement, the spindle was moved to the slack position in the same direction as the load to be applied. I did this as I thought it would be less error prone than attempting to set the machine to some notional zero position within the slack region. The additional deflection under the 5 kg weight was then measured. Backlash was measured by stepping either left or right in 1mm step mode, reversing direction and observing how much less than 1mm the first direction reversing step recorded. The steps per millimetre was set to 40.0 on the controller for this test to avoid any measurement complications. So here's the data plotted against position on the x-axis. The first thing to note is that there's quite a bit of variation in this data. Our noise floor appears to be about 0.03mm. Comparing our measured data with the predicted behaviour from the belt model, we have a chart showing the measured slack against the expected belt deflection for 1 kg rolling friction, that's the dots and line in yellow, and the measured deflection at 5 kilos against the expected deflection for the 50 Newton force, that's the dots and line in blue. The correlation is pretty good given the limits of the test precision, and it suggests our model is useful in capturing the basic aspects of backlash and force deflection behaviour in the belts. The y-axes are a little more complicated, as we have two of them acting together, one at each end of the x-axis. This means that the forward and backward forces are split between the two y-axis belts, but in a variable proportion depending upon the x position of the Z carriage. We can use the same belt deflection model as before, but this time we need to split the force across the two y-axes. We'll do this in simple linear proportion as we move left to right on x. We can now calculate the expected deflection of both y-plates for any position of the Z carriage on x. And this makes it quite clear the variation in forces on the two y-belts and stepper motors as x position changes. In the middle we have approximately double belt and motor strength, but at each end we drop back down to single. Using this, we can now calculate the combined effect on the Z carriage position. Initial comparison of this model to the measured data showed larger differences than I was expecting or happy to accept, which meant I had to think again about what else might be happening and then take some further measurements. I found that on the XL and XXL, the X-beam deflection is not negligible. Also, the front and rear steel plates were deflecting a measurable amount. We can calculate the expected deflection of the X-beam extrusion using some common engineering maths. We know the Young's modulus of aluminium is approximately 70 gigapascals, and we can calculate the bending resistance of the beam. We do this using the second moment of inertia, which is based on the cross-sectional shape of the beam. Using these numbers and applying a 50 Newton force in the centre of the X-beam, we get an expected deflection of 0.027mm, which is consistent with the approximately 0.05mm peak-to-peak I measured on my machine. Notably, if we calculate this for the short X-beam of the standard Shapeoko, the expected deflection is 0.003mm, almost 10 times smaller. The deflection of the steel vertical end plates at the front of the machine was also measured and found to be 0.05mm of 50 newtons. This is double the peak X-beam flex. As we found for the Y-belts, this also varies with X position as the force distribution alters between left and right. Incorporating the beam and plate deflections and then comparing the new model with the measured data, we have a reasonable alignment of the left and right deflections, with an error increasing slightly as we approach the ends of the X-beam. Comparing the Z carriage behaviour, we have a pretty good alignment of the modelled and measured data, and the slack is, as expected, very close to that on the X-axis. The Y deflection, as we've seen, is a bit more complicated than on X. We've seen how it varies with X position, but, as we already know, the belt deflection will also change as we move along the Y-axis. To understand this properly, we need to model what happens as the machine travels front to rear as well as left to right. We can use basically the same model we did for the X belt, just applying the appropriate share of force to each Y-axis. So, viewing the machine from this direction, we can plot the expected deflection of the Z carriage in the Y direction like this. The graph's showing the Y deflection in the vertical axis and as colour bands, and the surface shows, as the spindle moves around the machine in X and Y, and for the same force, how the Y deflection varies. We can see that the deflections are lowest at the front and back of the machine, and worst at the left and right ends of X, midway between front and back in Y travel. This model is within plus or minus 0.03mm of the measured deflections on my machine, so I believe it's a reasonable, if simplified, representation of the major effects. So, finally bringing everything together. We've measured, developed a model, remeasured, made a better model, and captured what I think are the major elements of deflection. We've also seen how various components of the deflection vary as we move around in the X and Y axes. It might be interesting to see how this all adds together into the overall deflection of the machine. To do this, I've used the combined model to plot the resulting deflection for various directions of force on the cutter. The plot shows the expected deflection for a 50 Newton cutting force with its direction rotated around in 30-degree steps. I apologise for the slightly ugly graphs, but I made them in Excel so that it was easy to share, and I'll post the spreadsheet for anyone who wants to use it. Remember that we're only plotting deflection in the XY plane of the baseboard, and we're not including vertical components such as those seen in the spindle nodding motion. First, we have the plot for the central position on the XXL. The orange box in the middle is the slack, and then we see the slightly oval deflection for 50 Newton force in blue. There's a bit more deflection in X than Y in this position. Now for the other positions. The plots are laid out as per the carbide motion compass points looking down on top of the machine. On the XXL, we can see the blue deflection plot becomes a lot more oval at the north and south positions as Y deflection reduces because we get close to the ends of those axes. Similarly, the west and east become more oval, but this time due to reduced X deflection but increased Y deflection. The four corners are about the same as each other with similar Y deflection to the centre position but reduced X. Comparing the Shapeoko 3 with the XXL, we can see that the standard machine, despite having the same V-wheels, outperforms the XXL by a significant margin thanks to reduced belt stretch and beam flex. Remember, this is not including baseboard bounce, and it's becoming quite easy to see why cuts that are achievable on the standard size machine are somewhat more of a challenge on the XL and XXL machines. Looking at the rest of the positions for the Shapeoko 3, we have a similar pattern but with smaller central deflection oval, as well as smaller, better controlled north, south, east and west plots. Interestingly, the four corners are very similar to the XXL despite that machine's higher deflections toward the middle of each axis. We can also take a look at what we might achieve with some upgrades that some of us may already be machining the parts for. Here's what the model says about replacing the V-wheels with linear rails on just the X-axis. The measured deflections from the Y-axis V-wheels are much smaller, so we're not including those. The change in behaviour is quite significant in both machines, mostly in Y, but likely to have quite a strong effect on vibration too, as the V-wheel deflections are physically close to the spindle. And if we took the next step and upgraded to 15mm wide belts, but with Kevlar or steel cores rather than fiberglass, we could reduce the belt deflections as well and get something like this. So that's what I've got so far. What are the next steps? Well, more measurements, clearly. It would be very interesting to see proper finite element modelling of the machine to look for the major vibration modes and determine where adding additional stiffness or damping might help the machine. It would be good to measure how much of the observed belt deflection is actually coming from the stepper motor, angular deflection, and update the model with this data. It would also be nice to properly measure a standard size Shapeoko and compare that with the XXL to see what the frame deflections, beam deflections, etc. really look like. I'd like to measure an XXL with the X-beam linear rail upgrade, and I'll hopefully be doing that quite soon. And I'd also like to measure some other belt options installed on the machine. Next time. I'll be learning how to machine aluminium by turning some nice 6061 plate into some upgrade parts for the machine, and bolting that to some nice high wind linear rails, and definitely voiding anything that's left of my warranty.